Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily lead code problem, and the problem's name is sum root to leaf numbers. Okay, so what you will be given is you will be given a root of a binary tree. Okay, so for example, this is the binary tree given to you, and containing only digits from 0 to 9. Okay, and each root to leaf path in the tree represents a number. For example, if this is the tree that is given to you, then in that case, first of all, let me quickly copy it to the board. Okay, in that case, what should be happening is right from you will be given address of this root or reference, you can say. So this whole path from root to a leaf node will represent a number which is by the way 12. And similarly on this side also there will be another number which is 13. So you have to return sums of these two numbers. Okay, how the number of the, leaf node is equal to the number of numbers that will be present. Okay, and you have to just basically return the sum of these paths. Okay, no matter how many paths are forming in the tree. So in this particular case it will be 12 plus 13, which is equal to 25. Okay, so if you see the result also, it's 25, and it's saying that from root to leaf path from 1 to 2 represents 12, and another root to leaf path is representing 13. So if we add these two, it will become 25. So this is what you have to do. Okay, so you have to return the total sum of root to leaf numbers. These cases are generated so that answer will fit in 32-bit integer. Okay, and it is also mentioned that a leaf node is a node with no children. Okay, it is the definition of the leaf node. I hope you are able to understand that there are no left or right childs for this particular one, and similarly for 3 there are no left or right childs. So these are the leaf nodes. Okay, so if we change color also, okay, these are the leaf nodes. So this is what the problem statement asks you to do. Now we will see how we can approach this problem. Before thinking of an approach, let's quickly have a look at the constraints also. So according to the constraints, the number of nodes in the tree is from 1 to 1000, and each value is ranging from 0 to 9. Okay, and it is mentioned that the depth of the tree will not exceed 10. Okay, so anyways, we will try to implement an approach that will be having time complexity of order of n, where n is the number of nodes. Okay, so let's try to implement that approach. So what we will be doing is, let me clear a little bit of the portion. Yeah, I think it should be fine now. Okay, starting from the very root, you will be having a variable. Let's call this variable, or I think it would be fine if first of all let's talk about the approach. We will come to the code or implementation part later on. Okay, so we will be having a variable. Let's call it current number. Okay, so what we will be doing is how we will be forming this whole number 12. That is the only thing that we are concerned. So I think taking the code to the board and explaining the whole logic is more efficient in terms of the time it will take for you to understand the approach. So anyways, let me describe it with the help of code only, because this problem involves recursion, so it will be a little bit easier for me to make you understand how things are working out here. So first of all, instead of that, let's resize it a little bit. Okay, so that the code should be taking major portion. Okay, this is the code, and let's remove this part. This is unnecessary. So this is the code in nutshell. Let me zoom in a little bit. I think it should be fine now. Okay, yeah, now it's fine. So this is the whole code, and let's see how we can approach this particular one. Okay, so what we'll be doing is, starting from the very first node, which is 1, we will pass this root node into the function find sum. Okay, and there will be a variable total sum, which we will be returning. So this find sum method updates the total sum. Okay, updates the total sum. Okay, and so how this thing will be updating the total sum is the thing that is having the main logic. So first of all, we will pass root and current number. Current number will be initially 0 because it is not having any kind of value right now. So what you will be doing is updating the current number as you traverse each node. Okay, so these are the base cases. We will look at them at the very end of the discussion of this particular logic. Now coming back to the main logic that is there. So this is the thing that is making us to keep track of the number, this 12. So first of all, current number is as of now 0. Okay, and since you are visiting the root node, so it will be updated to 0 into 10 plus 1. Okay, so current number will now be 1. Okay, so we are just having a simple logic. We are multiplying whatever is the value of current number right now with 10 and then adding the root value. Okay, so for example, when you will be visiting this 2, at that point current number will be 1, and it will be updated from 1 to 12 with the help of this logic. 1 into 10 plus what is the value of this node, which is 2, so it will be 10 plus 2, which is nothing but 12. Okay, and as soon as you reach a leaf node, you will hit up one of these base cases, this case to be specific, and you will update the total sum then and there only. Okay, and yeah, that's pretty much it. And you can also have a return statement also. Okay, and yeah, after that, let's say you are visiting the right hand side. At this point current num will be 1, so this logic will work out, and 1 into 10 plus 3 it will be, so it will be 13. And as soon as you hit a leaf node, then you will update your total sum. So this is the whole logic that is working behind this whole thing. And other than that, we are also taking care of this kind of case I mean, when things are going uh, okay, I mean, if you are at a node whose right or left child is not null and other child is null, in that case this thing will work out. I think this is not required maybe, so we can remove it, because this will anyways stop the recursion at the leaf node. Okay, but it will happen sometimes that your recursion will go to this node. Okay, so I think this is necessary, so we can keep it as it is, because for this node they will neither be a left node or right node, because this node is null itself. When recursion will be reaching this node, so we should be returning in that case. Okay, and so this is the whole logic and how things are working out here. And then you will recurse for left and right subtrees. Okay, and the time and space complexities, as you must have guessed, time complexity wise we are visiting each node only once, so it will be order of n, where n is the number of nodes. Okay, and space complexity wise it's just we are using recursion stack, so whatever is the depth of the tree, that much space we will be using. Okay, order of depth of tree. Okay, and in one of the constraints it was mentioned that the number of nodes in the depth of the tree will not exceed 10. Okay, so it's pretty much constant, you can say, so it will be order of 10, so you can take it constant. Okay, so this is the whole logic, and this is how things will work out. And if you are still having any doubts or any queries in general, then please feel free to ask them in the comment section. And I hope that this problem solving session added some value to your journey of owning your DSA skills. And remember, consistent practice is the only way to master DSA. And stay tuned for tomorrow's challenge, and I will see you in the next video. Thank you for watching.